Hello, ladies and gentlemen. My name is Ziyan Han from Beihang University, China. Today, I will present our work on graph entity matching and introduce it from 5 aspects. As we know, keys are fundamental integrity constraints. They have been extensively studied for XML and recently further defined for graphs. Keys for graphs are used to identify vertices. They are designed as a combination of topological constraints and value constraints. Here, the topological constraints are graph patterns. The entity matching on graphs includes 2 types. One is on a dirty graph, and the other is on 2 clean graphs. There are currently 2 types of methods, which are constraint-based and machine learning-based. The former generally obtain a set of high-quality constraints, and then use these constraints to perform entity matching on the graph. The advantage of this type is that they can provide interpretability, while the latter use machine learning to identify the same entity. They can provide state-of-the-art results for entity matching on the web data. However, there are still some challenges or disadvantages for those 2 types of methods. The constraint-based methods need to obtain a set of high-quality constraints beforehand, which can be given by domain experts, but it's unrealistic. They can also be automatically discovered, but it's not easy to. Even harder for the discovery of graph keys, because graph keys contain not only patterns, but also value constraints. They are both need to be discovered. And it's more challenging to define the similarity threshold for keys with attribute similarity. Well, for the other type, machine learning-based methods, although they perform pretty good, they are used as black box, so they lack interpretability for explaining why 2 entities match. Therefore, we want to combine the advantages of machine learning-based and constraint-based methods to get high accuracy and at the same time provide interpretability for the matching results. Since keys can identify nodes, so we aim to propose a supervised learning-based method by using keys as features. In addition to this, due to the noise and inconsistencies in real-life graphs, we relax graph keys with attribute similarity. Here we give an example to explain why we relax the definition of graph keys. As we can see, here's the movie knowledge graph containing person and movie entities. 2 graph keys phi1 and phi2 are shown on the right side of the picture. They are depicted as 2 graph patterns Q and Q prime. If we apply the first key phi1 on graph G1 via isomorphism, we can get the results that P5 directs M1 and P5 directs M3 due to the different names of M1 and M3, though we consider them not the same entity, which may be opposite to the fact, because M1 and M3 are directed by one director and have similar names. There's a great chance that they are the same entity. However, if we relax the definition of graph key phi1, change the equality in constraints to similarity, we may get the right result. Therefore, we relax graph keys with attribute similarity. Here's our problem definition. We treat entity matching as a classification problem and set the input to be a graph G and label the data D. We set the output to be the classification results for this data D. The D is the ground truth. It contains triples of 2 entities and a label. The label means whether 2 entities match in the real life. Next, we give the framework of our method. First, we propose graph matching keys, also called GM keys. They extend graph keys with similarity predicts on attributes. Then we propose a supervised learning method. It uses GM keys as features. We name this method GMK-SLAM. It consists of two major steps: feature extraction, which contains candidate GMK discovery and vector representation, and feature selection, containing feature ranking and feature filtering. Next, we explain each step in detail. First, we give the definition of graph matching keys. The left side of constraint X5 is a set of literal. It has two forms. One is variable literal and the other is ID literal. The right side is fixed in the form of ID literal. X0 and Y0 are the designated nodes. The pattern here are designed to be symmetrical. It consists of two patterns Q1 and Q2. And Q2 is a copy of Q1 via a bijection. The intuitive meaning is that when the topological structure around two nodes is similar, they are more likely to be the same node. After defining GM keys, we firstly discover candidate sets for them. Here we define the support of pattern. For a pattern Q, the support is defined to be the fraction of node pairs in data D that have matches of pattern Q in the graph G. We start with a single node pattern Q1. Then we expand it with one edge at a time. Just like the expansion using tree structure in the paper discovering graph functional dependencies. The pattern Q1 and its copy Q2 combine to form pattern Q. If the support of pattern Q is lower than the given threshold, then we filter this pattern. Otherwise, we reserve it. After we obtain a set of high support patterns, we form the graph matching keys by adding one potential literal to each pattern at a time. It greatly reduces the complexity because it avoids enumerating all literals. After getting a set of candidate GM keys, we use them as features to get the vector representation for the labeled data D. First, we give the definition of confidence of GM key phi on a node pair V and V prime. If this node pair can find matches of pattern in the graph, the confidence value is the similarity of their attributes from literal in GM key phi. Otherwise, the confidence value will be set to be 0. Intuitively, confidence quantifies the greatest possibility of node pair V and V prime, satisfying the literal L in GMK phi. Recall that each GMK has one literal. Then, using GMKs as features, for each node pair in data D, we can obtain a vector. The dimension of this vector is the total number of GMKs, and the elements in vector is the confidence of each GMK on this node pair. Therefore, at present, we have obtained vector representation for each node pair in the labeled data D. Using GMKs as features, we'll do feature selection to filter the GMKs with less contributions and obtain a set of high-quality GMKs. First, we calculate the Gini importance scores for each GMK in the candidate GMKs. Then we rank them from high to low and get a ranked feature list. Next, we use the ranked list to filter features. It starts with an empty feature set F. Then we run over the features in ranked list, add them to feature set F one at a time. Each time after adding a new feature theta, we retrain a classifier using feature set that contains feature theta to see if the performance improves. If so, we will reserve the feature theta. If not, we'll filter it. As we can see, here's an example to make the process more clear. At first, the feature subset F contains feature theta 4. Then we add the second feature theta 3. Retrain the classifier. If the performance improves, we'll next add feature theta 1. Otherwise, we'll delete the feature theta 3 and then add the next feature theta 1. We'll repeat the process until all features are traversed. After this process, the eventually obtained feature subset F is a set of meaningful GM keys. We'll use them to do entity matching. And we also get a classifier eventually. It is trained by the final GM key feature subset. We'll use them to do the prediction. If we are given a node pair, we can use this classifier to predict whether they are the same entity. Our GM key slam method can provide interpretability, since it uses GM keys as features. During the last process, feature filtering, we build a tree to explain the matching results. As we can see from the picture, the right nodes in the tree are feature nodes. They are the features in ranked list. The left nodes in the tree are match nodes. They store a set of nodes. These nodes are predicted to be matched for the first time once the feature in its father node is used for training. By analyzing this tree, we can figure out to decide whether a pair of nodes match, which features are necessary. We experimentally evaluated GM key slam for the effectiveness and the interpretability using 6 real-life graphs, and compare our method with 2 machine learning methods. They are Deep Matcher and Magellan. Here's our results. We use precision, recall, and F1 score to evaluate the performance of those methods. As we can see from the table, for these 6 graphs, GM key slam performs better than the Deep Matcher and Magellan in general. For interpretability of GM key slam, we give an example of experiments here. As we can see from the tree, we can conclude that Airhand ROM and EROM are the same one, only by their similar titles. But it's not enough for Lwu and Langwu, unless we consider their co-author's name at the same time. To briefly summarize, we first propose graph matching keys named GM keys, and then we propose a supervised learning method named GM key slam. It uses GM keys as features. Our method can provide interpretability by building a tree. Through experiments, we have verified the effectiveness and the interpretability of our method, GM key slam. For the future work, one topic is to develop efficient algorithms for discovering keys, and another topic is to adopt keys to various applications with different pattern matching semantics. That's the end of my speech. Thank you all.